So here we have been given a LPP, that is z is equal to 0.5x1 plus x2, and we have the constraints like this. Then we have to find what kind of solution we are going to have for this LPP. Okay, so in order to solve this, we first try to find the max set. This is the given things. Then we try to plot the graphs. And after plotting the graphs, we can see these are the boundary points. So we are going to find all these points, and then we are going to check the value of this constraint on that points, and then we can see that this is the particular point, and the maximum value of z is given by 5. Okay, let's move to the next one. Okay, so the matrix has been given, the minimal polynomial has been given to us. We have to find the matrix, right? We have to find the equation of the matrix. So the minimal polynomial is given by t cube minus 8t square plus 5t plus 7, and the matrix associated with it is given by a naught plus a1x plus a2x square plus an x to the power n, where a is what? 0 minus a naught, 1 minus a. And then a is given by a1, a2 dot 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 a minus 1. So I is your identity matrix, and from there we can say that this a is going to be our matrix, right? Okay, let's move to the next one. So now we have been given that consider the following statement where we have x and y are n by n matrices with real entries. Then which of the following is and are correct, right? That Pn was xp is a diagonal matrix for some real invertible matrix P, and we are going to get a basis Rn which consists the eigenvectors of x. If x is a diagonal matrix with distinct diagonal entries, and we have that xy equal to yx, then we have that y is also a diagonal matrix. If x square is a diagonal matrix, then x has to be a diagonal matrix. If x is a diagonal matrix and you have that xy equal to yx for all y, then x equal to lambda I is going to be for all lambda belongs to R, right? So we have that eigenvalues are not needed here, right? We can simply put it that we can simply get the, we have to simply consider xy, where x is a diagonal multiples of the rows of y by the diagonal entries of x, and yx has the same with y's at the columns. Now ij entries of xy and yx are these. Now if you have xy equal to yx where I is not equal to j, this implies that y is diagonal. Again, since we know that x is of distinct diagonal entries, which means that the distinct eigenvalues we have that x is diagonalizable, then x can be written as P inverse xp, where P is the matrix whose columns are the eigenvectors of x. And from there we can say that option A is going to be our correct option, right? Okay. Which of the following statement is correct? A closed set either contains an interval or else is nowhere dense. The derived set of the set is a closed. The union of an arbitrary family of closed sets is closed. The set R of real numbers is open as well as closed. So we have to check which one of these are correct, right? Okay, so we know that the theorem says that a closed set either contains an interval or else is nowhere dense, right? So if we have A to be a closed set, and since A is nowhere dense in R, and it is happening that A is nowhere dense in R, not nowhere, then we are going to get an interval I such that this I1 is a subset of I, and I1 intersection A is not equal to phi. Then we have I is subset of I, and then for theorem B we have the derived set of a set is a closed set, right? So from there we can say that suppose S dash is the derived set of S, then we have to show that the derived set S double dash of S dash contains S dash, right? Then S dash is the derived set of the set S. Then we have to show that S double dash of S dash contained in S dash, right? Now if we take S double dash to be our empty set, where S dash is either a finite set or an infinite set without limit point, then the S double dash is equal to empty is going to be a subset of S dash, and therefore we have S dash to be closed, right? Now, if it happens that S double dash is not equal to empty, we are going to take a j, which is an S double dash. Then j is a limit point of S dash, and every neighborhood of n of j contains at least one point of S dash, right? Now, eta is a point in S dash, and eta has to be a limit point of S dash, and every neighborhood of eta, that is n being such a neighborhood, contains infinitely many points of S. Every neighborhood in xi contains infinitely many points of S. So from there we can say that the xi is a limit point of S. Now the set R of real numbers is an open as well as closed set. The set Q of rational numbers is neither open or not closed. That is known to us, right? So from there, we can simply show that an open interval is an open set, but a closed interval is not an open set, right? The next theorem is to have that a set is closed if and only if its complement is open, right? Suppose if you take A to be a closed set and B is a complement of this set, then we are going to show that B is an open set. Now, if you take an element X from B, so if the element X is in B, obviously X is not in A, right? So we are going to get so it is not going to be a limit point of A because it's a closed set. A closed set contain all its limit points. So since X does not belongs to A, so X is not also a limit point of A. That means we are going to get a neighborhood of X. So you're having an X and you're going to get a neighborhood of X such that no points of this neighborhood is contained in A, right? So that means what? If no points of this neighborhood is contained in B, then this neighborhood is going to be contained in B, right? So from there, we can say that B contains a neighborhood since X is an arbitrary element which we have picked from B, and we have shown that if we take the neighborhood of that point, it is going to be inside B. So from there, we can say that B contains the neighborhood of every point because we have taken in consideration an arbitrary point, right? Now we have that C is an open set and D is its complement. We are going to show that D is a closed set. So what we have done earlier, we have taken E to be a closed set, and since we are considering D to be the complement of it, we have shown that D is an open set. Now we are going to prove the converse of it. That if C is an open, then its complement is going to be a closed set, right? Now X be a limit point of D, we can take X to be a limit point of D. Now, if we take X to be an element of C, then we are going to get a neighborhood of X contained in C, and thus it contains no point of D. As such, X cannot be, and from there we can say that X cannot be a limit point of D, right? Thus, from there we can say that no point of D, no limit point of D can belong to C, and hence we can say that D is a closed set. Okay. Okay, let's move to the next one. Okay. Which of the following satisfies the Rolle's theorem? So we have to verify which of these are satisfied by the Rolle's theorem. So if you look into the problem A, we have been given f(x) equal to sine x, and this sine x is continuous and differentiable in the interval that they have given us. Now f dash x exists. Now if we take 2 points, then we are going to get a point rho in between 0 and 2 pi such that at that point the f dash x is going to be 0, and hence we can say that f(x) satisfies the Rolle's theorem. Okay. Now the line integral integration c1 plus x square y ds, where the curve c is given by this rt is equal to sine t I cap plus cos t j cap, and then we have to find the value of the line integral, right? Okay, so if you have integration c1 plus x square y ds, then rt is given by sine t plus I cap plus cos t j cap 0 less equal to t less equal to pi by 2. You have x to be sine t, y to be cos t, then dx is equal to what? Cos t, dy is equal to minus sine t, then ds is going to be what? Root over dx square plus dy square, right? So ds is given by root over sine square t plus cos square t. Now, if you want to find the value of this integration 0 to pi by 2, 1 plus sine square t cos square t root over sine square t cos square t dt, because ds has become this value. We simply solve the integration and we put the value of the limits. We got it to be pi by 2 plus 1 by 3. So it's a pretty easy problem. Okay, let's move to the next one. Suppose u is a homogeneous function. So u is a homogeneous function of degree n, and then that is given by this. So this above statement is the statement of which theorem? That is what you have to verify, right? So since u is a homogeneous equation function of degree n, and this is what we are getting, so from there we can say this is an Euler's theorem. So you have to remember the theorems as well, right? Okay, now you have been given that u is equal to log of x cube plus y cube plus z cube minus 3xyz. You have to find, and this is also have been given, you have to find the value of m square, right? So you have to find all the partial derivatives here. So this is what they have given us to be u. Then del u del x is what? 1 by x cube plus y cube plus z cube minus 3xyz into 3x square minus 3yz. Del u del y is this one, and del u del z is this one. Now if you add them, it should be equal to some m over x plus y plus z, right? So we do it, we get that m is equal to 3, and from there we can say that m is going to be 9. So it's nothing but simply a calculation. Now here we have the differential equation is given by this. You have to identify what kind of differential equation is this, right? So this is not if you look into this, this is second order because the highest order here we have is second order. And this is not linear because if you look into this tan of x plus y, so you are having a y as well within a tan, right? So it is not a linear function. Homogeneous or non-homogeneous, obviously it is not homogeneous because if you look into this term, it is a non-homogeneous, right? So from there we can say that this differential equation is non-homogeneous, and hence we can say the second order non-linear non-homogeneous equation. Okay.